Okay, let's make a start. Right, go to your checkpoint. If you haven't done it, you better start doing it. We'll go over some of the questions. There can never be any progress if you don't do any homework. Okay, we have done this one. Right, you can try doing this one. The figure below shows a mass M at the end of a horizontal spring performing simple harmonic motion with a constant amplitude 10 cm. Maximum kinetic energy of the mass is 80 joule. What is the distance of the mass from the equilibrium position when the potential energy is of the system is 40 joule? Yep. What am I going to do?
Kinetic energy.
What should I do? There are some formulas there.
1/2 mv square.
1/2 mv square. Where is your v? How to find v?
Yeah, don't have v. Don't have v.
How to find v?
Oh, yeah lah, F equals to 1/2 mv square lah.
No v. No v is given. Right? No v is given. What formula to use? Right? Remember, it's easier to work with potential energy. That's why they ask you potential energy. Kinetic energy is always harder because you have to use this formula to find the kinetic energy. Right? You have to replace your V with that. So it's better to use kinetic energy. Go to this one. This is maximum potential energy. This is also total energy. This is also maximum kinetic energy. Right? And then you can use this one. It's simple formula. Like your energy stored in the spring. Okay, so choose the formula. This total energy or maximum potential energy is half m omega square a square. A is the amplitude, right? So you are given 80. So that is also equal to maximum kinetic energy, right? Same formula. And you are interested in potential energy. So what are the variable? Variable is your u and your x. That's your x. The others are constant, not given. Right? The others are constant because you use the same spring, you use the same mass. You change the amplitude, that's all, or change the displacement. So that's why I treat this as my x squared, take the u down, the others are constant, get a formula for that, and play with it. This is the new one, this is the old one, right? And then your x2 is x1, right? Square root of this one becomes x1. This one u2 take across there is u2 over u1, square root that. So your final, you are told what is the distance of the mass from the equilibrium position when the potential energy is 40. Right? So final is 40. Final is 40. Initial is 10 cm. So you put 10 cm, your answer will be in cm. Then u1 you are told is your, right? This is the amplitude. So that u1 must be the maximum potential energy or maximum kinetic energy is the same thing. Right? Maximum kinetic or maximum potential is the same thing. Right? That's why we are using maximum potential energy. And use your calculator, 7.07 cm. Okay. It's okay. Let's go to the next one. This one, what's the answer? Which of the following statement about critical damping is true? Yep, what's the answer?
Donkey.
Okay, good. Right? No energy is lost, wrong already. In any
Decreasing amplitude.
right? In any damping system, energy is lost because it's work done against friction. Only a few oscillation is possible. This is light damping or under damp. System takes a infinite time. This is heavy damping. Right? So your answer is donkey. True, correct, good. Number 2, a body performs damp oscillation if it is under damp. Which of the following is true? Right? Under damp or light damping lah. Yep.
Boy.
Period of damping, period doesn't change. Right? False damping does not affect the period. Total energy decreases exponentially. Yeah, that's a possible answer. True. Amplitude of oscillation remains unchanged. No, this is undamped. Right? It should be decreasing exponentially. The angular frequency increases. Angular frequency is constant. So false. So yeah, right. Boy. Good. Okay, number 3. Which of the following experiences critical damping?
Donkey.
Okay.
Oh.
Okay, we use it in ammeter. The pointer is critically damped. We don't want it to oscillate. Right? We want to read. We want it to point at the value and then we read. We don't want to oscillate for a while and then read. Too long time to read. Okay. Explain why the amplitude of the oscillation of a simple pendulum decreases with time. Yep. Yep. Okay, damping. What is damping? Presence of resistive force. Right? So the amplitude decreases because there's work done against air resistance or resistive force. So the total energy decreases. Right? So as the bulb oscillates, it does work against air resistance. Total energy decreases as energy is transformed to other form. Right? So the amplitude decreases. Okay. Right? Second part is just memory work. That's all. Right? Amplitude is this line. Displacement is this line. Okay. On the same axis, sketch a graph of displacement against time for oscillating system which experience undamped, critical damping, and overdamp. Right? This is memory work. You should be able to do it. Right? This is critically damped. This is light damping. This is overdamp. Okay. Memory work, nothing much about that. Let us go to this one. The figure shows a simple pendulum. The frequency of oscillation is F, is vary by varying its length. The amplitude of oscillation A for each frequency is recorded. Which graph shows the variation of amplitude A with frequency when damping is increased? Yep. What is the answer? Yep. What's the answer? Right? When damping is increased,
C, teacher.
say again.
C.
No, you increase damping, the amplitude should go down. It's poorly
Oh,
drawn.
so
A is also
A,
poorly
A,
drawn.
A, A, A.
A is also poorly drawn. Right? Let me just review with you why I say A is poorly drawn.
You say B is poorly drawn.
A is poorly drawn. The answer should be quite close to A, but A
Oh,
is
you put here
poorly drawn.
answer B question mark poorly drawn. That I can see here.
B also poorly drawn. Right? Even the book give answer as B, but it's also poorly drawn. The amplitude should go down, and it shouldn't touch each other.
Yeah.
Right? Shouldn't touch each other. Let me just review with you. Once a while they make mistake there. I can try the others while I get the slide for you. Okay, that's how it should look like. Right? They shouldn't touch at all. This one shouldn't touch at all. Okay, it's doesn't go to zero. It's this one always decreases lower than this one. This is for under damp. This is for heavy damping. Okay? Yeah, that peak there is less than your natural frequency. Right? Keep that in mind. Okay, let's carry on. Okay, number 2, an oscillating system is critically damped. The body in the system is displaced from the equilibrium position and then released. The body returns to equilibrium position. Yep, what is the right answer?
Don't know, sir.
Say again.
Don't know, sir.
I didn't revise. A, shortest possible time, a quarter of the period. Right? After a few oscillations, that one is light damping. Its amplitude decreasing linearly, then no such thing. Right? Amplitude decreasing exponentially to 0. That's for under damp or light damping. Answer is A. Okay, what's the answer for this one? Simple pendulum has a light polystyrene ball sphere as a box. Is forced into oscillation in air at different frequency. The variation with amplitude of the oscillation with frequency is shown in the figure. That's the figure. Which of the following graph best represent the result if the experiment is repeated in vacuum? Yep. Memory work only. Right? It shows you have not revised yesterday. We went over with you yesterday. Yep. What's the answer? Donkey. Amplitude is infinite. Nothing to stop it. Right? No air resistance. Nothing to stop it. Okay. Okay, number 4. The figure shows a mass M at the end of a spring. That's your spring. That's your mass M being forced into oscillation when the NO of the spring is set in vibration. Right? This one is vibrating up and down. The amplitude of oscillation of the mass M is maximum when the frequency of the vibration of O is F naught. If the mass M is substitute for a large mass M, the amplitude of oscillation is, okay, what's the answer? Yep. Right? If you use a larger mass, same material, it's likely they have larger surface area. Right? This is a poor question. So you have to assume that there's greater damping. Okay. So larger mass, using this formula for spring, larger mass, the period is going to increase. So the frequency is going to decrease. Right? Natural frequency is going to decrease. Greater mass, smaller natural frequency. So the frequency of driver is equals to natural frequency of the vibration of the load, and spring, the mass vibrate with large amplitude. The answer is B. Okay. Anything that you are not, that I didn't explain clearly?
Okay.
No problem. Then we go to the next one. I think we won't bother about this one. Memory work only, nothing much. Okay, let's try some focus. Before we end, we just do a few questions. After that, we will end for today. Get you warm up. I can try now while you wait for me to get the PowerPoint. Try yourself. Okay. Okay, focus 19. Very slow. Okay, all these things you must know your fingertips. Right, make sure you try the question. I will be spending half an hour next week. Okay, what's the answer for this one? A particle performs simple harmonic motion
Boy.
and its displacement from the fixed point O at time t is y. The acceleration of the particle is given. Which of the statement about the motion of the particle is correct? The value of k is constant, correct? The acceleration is always negative. You cannot say acceleration is negative. It doesn't make any sense. Right? It's always opposed to displacement. So it cannot be true. The velocity is directly proportional to displacement. No. Period of motion depends on y. No. Right? For a system, the period is constant. So one is true. Right? B, you cannot say it's always negative. Sometimes it's positive, sometimes it's negative. It depends on the direction of the displacement. Right? It's an ellipse, so it's not a straight line. That's why it's not proportional for velocity. False, y is a displacement. Period depends on k. Right? Depend on k. Answer is A. Okay, this one. A load of mass m at the end, of a vertical spring of force constant k performs simple harmonic motion of amplitude A. The maximum speed of the load is given by. Okay, how to calculate your maximum speed? Since you got so clever this time to get the answer so fast, how to get the maximum speed?
Oh no, this one I memorized.
There got memorized one. Exam there got memorized one.
I always see A square
You
root
look at
K
the
over M.
answer.
No, I didn't look at the answer.
How to
I
calculate?
always see this answer in the school, they always write. So I know
Oh,
that
like
was the
that
answer.
Cannot memorize one. Too many things to memorize. How to calculate the maximum speed?
Negative APG over M.
Negative what?
A times density times G over M.
Where got density? Remember circular motion. Same formula. That's your period. For the spring, there's your period. You must memorize the period. And then your omega. Omega is 2 pi over t. Right? So replace your t. Right? T is this one. 2 pi at the bottom there. Cancel off. So this one become inverted. That's an omega. Right? So maximum speed is, remember your circular motion. Right? This is your radius, your amplitude, omega. And put in your value there. A there. Okay. Can? Don't memorize. There are too many things to memorize. Yeah, fortunate because your teacher just did with you. Okay, let's do one or two more. This one, I don't think we will bother about this one. This one depends on your SPM work. Don't think they will try to be so cruel. How about this one? Yep. How to calculate? How to read? What is the frequency and kinetic energy of a object when the displacement is 3.0 meter? No, this one need to know how to read the equation given. This equation. That's the mass given. That's your displacement. Okay. How to calculate the frequency? Hey, make sure you do your homework. If not, you are not going to learn anything. After I teach you, you've forgotten already. After I teach you, you must do the homework. Spend another hour. That's the most efficient one to study. Revise through. It's still fresh in your mind. Do the checkpoint. That's how you force it in. After a few days, you forgot. After 1 week, you forget everything already. That's why you're having problem. That cannot be progress for you if you don't do anything about yourself. You have to learn your weakness. Yep. Frequency can be obtained from here. Right? That's your standard formula for simple harmonic motion, where the object start from rest. Right? Omega is 100. Amplitude is 5. You should be able to read. Omega is 100 radian per second. From there, you can calculate your frequency. Omega over 2 pi. 100 is omega over 2 pi. Use your calculator. Right? Kinetic energy. Yeah, you can think of this is your maximum kinetic energy or maximum potential energy, if you like. Right? If you don't want, you can use a velocity formula, right, to derive it. But that's my way of doing it. Easier to remember. Right? Same. You use velocity formula. That's your mass. Right? That's your total energy. Total energy A. Then potential energy is just your m omega square x square. That's why I use that. If not, you use velocity straight away. Half m omega square, still the same thing. Right? Then use this formula. So I say it's a matter of choice. Right? This formula. And then half mv squared. Sorry. Okay. Then put in your value. Right? There's a total energy. This is a kinetic. This is a potential energy. And put in your value. Mass is 2 kilogram. Omega is 100 square. A is 5. Right? It's in meters, so no need to convert. And then this is 3. X is 3. Displacement. Okay. Any comment? Okay. 1 or 2 more questions, then we will stop for today. Ooh, give you the answer already. What's the answer for the next one? Okay, what's the answer? Two bodies P and Q are oscillating with initial displacement x naught. The variation of the displacement x with time is as shown on the graph. A cohesive force with frequency F is then applied to P and Q. Which graph shows the variation of amplitude for P and Q with frequency F? Okay. What's the answer?
A.
Okay, let's go over that. Q, you should be able to read from the graph. Q is of greater damping compared to P, right? Amplitude smaller compared to that amplitude. So it means greater damping. Natural frequency do not change or change slightly. to lower frequency. Right? So Q will be at Q is greater damping, correct? P is light damping. How can it be A? How can it be A? It should be slightly shifted to the left. Right? Slightly shifted to the left. Slightly shifted to the left. Q is of greater damping. Okay, I think the best is A. Okay, the best is A, or shift slightly to the left. Right, amplitude shouldn't touch each other. Right, shouldn't touch each other. Okay, we do our last one. This one. The variation of displacement x with time for simple pendulum is shown in the graph. The expression for the above motion. Yep, what's the answer?
A.
Right, there's your cost graph. A is 0.4. Period you should be able to read. Right, period is that's maximum to another maximum is 0.4. Then you can calculate your omega, 2 pi over t, put in your t there, get 15.7. Then you can rewrite that equation, minus 0.4, right? This is a minus cost graph, 15.7 t, right? Or equation there, unless you are, right? So you have to use a bit of your maths. It's a bit tricky. Okay. B or note, right? You just use this equation, that's all. Can? So cos A minus pi equals to minus cos A. Can? If can, we'll stop for today. Make sure you do your homework and then tell me when you want next week. Any question? Anything not clear? Yep. Any question?
No, so far okay je.
Okay, then we'll stop for today.
Yep. Thank you.